Okay, so before the break, we have talked about a functional scalar linear model, so we learned that in order to control the smoothness on the coefficient time functional parameter beta t, we want to express the beta t as a linear combination of the basis functions. So yes, so now let's move on to the last scenario for functional model. Is also the most complicated function linear model. So we have learned the first two scenarios when the response is a scalar and the predictor is a function. And second scenario, the response is a function and the predictor is a scalar. So now the work on the last scenario is when the response is a function and the covariate is a function as well. Okay, so for this scenario, we actually also have two cases to study. So the first case is we call a concurrent linear model. So basically here we will predict the YIT based on the current values of covariate XIT. So this is how the model looks like. You can see here the value of the response yi at time t will only depend on the current value of predictor xi. So that's why it's called a concurrent linear model. So this model is very simple, but at the same time you have to have a strong belief that the xi, the predictor xi, x can have an instant effect on the y. So there's no lag effect. So this is kind of very strong assumption. So you have to be careful when you're using the concurrent linear model. Okay. So how do we do the estimation? So basically, we still will minimize the sum of the integrated error, and so here we will also estimate express the beta t as a linear combination of the basic functions. Sorry, here should be have a node j here. So then we can write down the basis coefficient by this least squares estimator, and so again here you see that there's no roughness penalty roughness control. So what we typically do is we will add in another roughness penalty, and so which typically will define as the second derivative on the beta t. So this is the it's very similar to the function scalar regression. Okay, so now let's look at a more interesting case. We call it general functional response model. So basically, for the concurrent model, it assumed that the predictor, the response y, will depend on the predictor x simultaneously, right? So this is a little bit strict because we know that in many applications, the value of the response may depend on the value of x, not only depend on the current time, maybe we also depend on the history of the time. for example, I have working on the how the temperature affecting the forest fire. So we know that so the forest fire will not only depend on the temperature or the precipitations at the current day, it will also depend on the weather in the past, right? So there's in many cases, there will be always some kind of cumulative effect or historical effect of the predictor on the response. So so what we do is that so basically the y at each time t will depend on the value of the function over the whole interval, right? So so if we want to write down this model over all time, then we can write down the model as yt equal to alpha t plus the integral of beta st xs ds plus epsilon t. Okay, so here you can see that we have a bivariate function beta st. So this beta st represents the effect of the x at ts on the value of the response on the value of y at the time t, right? So now you can see this model is more general. Okay, so it can handle the lag effect or historical effect of x on y. So this is the most general case. So basically, the value of the response y will depend on the value of the x on the whole time range. Okay, but sometimes this is not realistic either, because we know that typically the response yi will only depend on the predictor before the time t, right? So so for example, the weather today should not affecting the yeah I'm wrong. Oh, sorry. What did I see? So the forest fire today will only depend on the weather before today, right? It cannot depend on the weather after today. So therefore, we can have the historical linear model 1. So basically, yit will only depend on the value of xrs when s is less than t. Okay, so this is the we call it historical model 1, and so basically in compared to the general function regression model, we will set the beta st equal to 0 when s is greater than t. So in that case, it will be a little bit harder to estimate. We will require triangular basis functions. The second historical linear models, I think, is also my favorite function regression model, is that we will restrict the dependence of the response yi on the predictor x at a short time windows. So you see here, the first model will depend on the y will depend on x from 0 to t, right? So in many applications, the response will only depend on the predictor up to a short windows. For example, the forest fire will only depend on maybe the weather in the past 1 month, right? So it cannot depend on the in the past like 2 months, 3 months. It's too far away, right? So this delta here represent the lag effect. Okay, so this is a more realistic model for many applications. Okay. So any questions?
A small question.
Yes.
So how do you decide the size of delta?
Yes, so this is a very good question. How do we decide the size of a delta? So generally, we can try the different candidate values for delta, and we can do a test, right? So this is one way to do. The second way is that actually we have one recent paper and to estimate this delta automatically. So we can get a sparse estimator for the beta ST, and we can identify this delta automatically. So we will find out in which range the beta ST will be equal to 0. Yes.
Thank you.
Yes, that's a very good question. Okay. So so now let's go back to our general functional function regression model. So basically here we have this bivariate function beta ST to estimate. Okay. So what we can do is we still will estimate the beta ST by minimize the integral squared of the fitted error. And then we will represent the beta ST as a tensor product of two basis functions. So phi j and psi k are two basis functions. So so they typically will be one-dimensional basis functions. So psi and psi can be the same or can be different. So generally, we will treat the phi and psi to be the same basis functions. Okay, so if we have this tensor product to represent a beta ST, we can write down the beta ST as this form. Okay, so you notice here we have this vector of the basic function phi s and the vector of the basic function psi t on two sides, and we will have a j by k basis coefficient matrix B in the middle. Okay, so now we want to estimate the basis coefficient matrix B here, and by minimize this sum integrated of square error. So then we can plug in the formula for beta ST into the integral, and so then so we will have this form, and so you can see here this B basis matrix, coefficient matrix, and psi t will not depend on S, right? So only the phi s and xis will depend on S, right? So we can take these two terms outside the integral. And so then we know xis, we know the basic function phi s, so then we can calculate this integral and get a zi. Okay, so then we will have a zi times b times phi t, and then we can estimate. We can write down the model. So we write down the integral in this form, and then we can write down this complicated integral model by this vector form. Okay. So then we write down as this vector matrix form. So the only thing here is that this B is in the middle, right? So we know that if we want to do the least square estimation, the B had to be on the right side, right? So what we can do is that we can using this formula. So this is a formula for the so when we do the vectorization of matrix A times x times e, we can write down as in this form. Okay, so you can see here by doing this, this middle x matrix will go into the right side. Okay, so this is a very important trick to do. And so inside, this is called a Cronach product. So if you're not familiar with the Cronach product, this is the definition. So Cronach product basically is if you have a matrix M times N matrix, and B is a P times Q matrix, A Cronach product of B will become a PM times a QN matrix. So basically in this matrix, it will become the product of each element in A multiplied by each element in B. Okay, so it's a big matrix. Okay, so so if we have this form, then we know that this Z transpose B times psi t will be just a vector, right? So then this vector will be equivalent to vectorize this vector, right? It's the same. Okay, so then we can write down this vector of B to the right side. Okay, so now we have this form now. Okay, so this psi t is known, is a vector of the basis functions, and z is also known, and so then the whole thing is known, and then we can estimate the vector form, vectorize of the coefficient matrix B by doing the least squares. So so you can doing the least squares, and you will find out that the vector of the basic, the coefficient matrix B will be in this form. Okay, so it's a little bit complicated, involved a lot of two Cronach product, but here generally we know Z is known, psi is known, Y is known, so we can calculate the vectorize of the coefficient matrix B by this formula. Okay, so this is how we estimate this. After we get the basis coefficient B, then we can so then if we know B, we will get the beta ST, right? Yes. Okay. So this is how we do the estimation. So now let's go to functional time series. So actually, Xiaoling asked me in the beginning that how the functional time series is different with the time series. So here, basically, functional time series is a time series of functions. So we have y1t to ynt. Okay. So after we have this time series of functions, then we can using the classic time series model to model these functions. So here this is the functional ARP model, and so you can see here basically we treat the Yij t as the predictor, and then Yit as a response. So we will estimate the basis, the coefficient function beta j. Okay, so we do the estimation, and for this is actually, you can see here actually is the same as our general function regression, right? Yes. Okay, and for the we can also doing the functional ARMA model, and so in that case it will be also very close to our so basically we treat the Yij as the predictor and Yit as the response, and then we will have this functional ARMA models. Yes. So this area is relatively new, and if you I think there'll be a lot of open problems here. So yes. So here is a summary for the function regression. So you can see that for function regression, we have many versions models available, right? So it depends on how your application looks like, and what kind of assumption you want to make. Okay, so function regression model can be very general, very different. And so generally, we need to estimate a bivariate coefficient function. And you can see from the formula, it is more complicated. And it have to using the tensor product or basis function to represent the bivariate coefficient function. And so this function regression model can be extended to functional time series analysis. Okay, and so we also have some restricted model it's more realistic, but also harder to code. Okay, so this is the result, the function regression model. Let me stop.